Brian, and he will also be talking about verification, but this time instead of heaps, he will be talking about verifying monad transformers.
Okay. Yeah, so in this talk I'm going to talk about some verification work that I did in the Isabelle theorem prover with monad transformers and some of the tools that I developed to help with that effort. So basically the motivation of this work is to reason about code that uses type classes with laws. So the common example of that in Haskell might be class ORD, fixes an operation like less than or equal. And informally in Haskell, people usually assume that these operations will satisfy some additional properties. So for example, with ORD, we would assume that the ordering is actually a total ordering. And so then, having classes like this, you can implement code, functions, and libraries that are parameterized over an arbitrary ORD instance. For example, you can have a library of balanced search trees or a sorting algorithm. And usually the correctness of this code actually depends on those informal laws. So if you use the generic function at an instance that satisfies the laws, it works correctly, and otherwise the generic algorithm may break. So we want to figure out how to reason about this kind of code formally. So the theorem prover that I'm using is Isabelle Hall. So it's an interactive theorem prover, and it uses higher order logic. It has a type system that's really similar to standard ML. But in addition, it has overloading and axiomatic type classes. So basically, you can define a type class in a very similar way to Haskell, where you declare a class and you give the list of operations. But in addition to the operations, you can also give a list of the axioms or laws that those operations are supposed to satisfy. And so then later when you provide an instance of one of these classes in Isabelle, you not only have to provide the definitions of all the operations, but you also have to provide proofs that the operations in that instance satisfy all the laws. And so then on top of Isabelle Hall, there's another library that I've spent a lot of time working on called Huffman CF. This is high order logic plus LCF, which is Dana-Scott's logic of computable functions. So this is designed for reasoning about lazy functional languages like Haskell. Basically, it's a formalization of domain theory, and it provides a couple of tools that let you do new kinds of definitions in Isabelle. So Isabelle Hall, it only comes with automation for defining inductive data types. But Huffman CF also provides another package called a domain package, and this lets us write data type definitions that are pretty much just like Haskell data definitions. We can have lazy data types. Those data types will contain bottoms, partial values, and possibly infinite values. Similarly, Huffman CF has a package that extends the kinds of function definitions you can write. So while Isabelle Hall only has support for provably terminating functions, in Huffman CF we have a package called fixrec. This lets us write arbitrary general recursive functions, just like you can in Haskell. You don't have to prove termination, so you can have functions that don't always terminate. They might evaluate to bottom. So using these tools in Huffman CF, plus taking advantage of the support for type classes in Isabelle, we can already reason about quite a large variety of Haskell code. For example, the balanced search trees or the sorting algorithms that are parameterized over a type class like ORD. We can actually do completely formal proofs in Huffman CF where the proofs actually rely on the class axioms for the type classes involved. But there are some limitations, unfortunately, because basically Isabelle's type system is not as sophisticated as the type system of Haskell. And where you really run into this problem is when you move from regular type classes to constructor classes. So for example, the functor class fixes the function fmap, and usually there are two laws that we want to assume, that fmap preserves the identity and composition. But if we make everything explicit here, there's really both polymorphism in the type of f map itself. So it's quantified over type variables a and b that do not occur in the class predicate. And also the class axioms are polymorphic, so we're really asserting that these laws hold not just at one type instance, but over all possible type instances. And so Isabel's type system doesn't support any of this. So Isabel, in a type class definition, you can't have any extra polymorphism in your class constants. So the only type variables you can mention in the type of a constant, you can only have one type variable, which is the class parameter. Also, class axioms, you can't state type quantification. Type quantification is not expressible in Isabel's logic. And actually, Isabel, you can't even express type variables of higher kinds. So in Isabel, all type constructors have to be fully applied, and type variables can only stand for types. So this is a problem. So what are we going to do? One possibility is, well, we could just give up on higher order logic and switch to a logic that has a fancier type system. All right, so we can use a dependently typed logic like what's available in COP or AGDA. And in those systems, it's certainly no problem to do quantification over types or anything like that. Or if we want to stay closer to higher order logic, there's a recently developed system called Hall Omega that adds type quantification and other features to higher order logic. But if we did that, then we would give up on a lot of the nice features we have in Hall CF. So we would give up on being able to reason about lazy data types, bottoms, general recursion, least fixed points, and so on. So it would be nice if we could reuse all the infrastructure that we have in Hall CF. So the approach that we went with was we'll just use domain theory to essentially simulate all those missing features of Isabel's type system. So using some domain theoretic concepts, in particular, a lot of these involve using a universal domain type. We can emulate all the features that we needed to reason about type constructor classes. So type variables of higher kind, class constants that have polymorphic types, and then class axioms that use type quantification. And so all these things are implemented in a library that's available for Hall CF called the Tycon library. So the first step is how do we reason about types and type constructors? So in Hall CF, there is a class of representable domains, which are basically the class of all types that can be embedded into the universal domain. And so this class comes with embedding and projection functions to go back and forth. So the domain package in Hall CF, it uses the universal domain to construct data types. So every data type that you define in Hall CF is automatically a representable domain. So essentially what this means is that any type in Haskell of kind star maps onto some type in Isabel in class rep. And so in the Tycon library, we kind of push further on this mapping of Haskell kinds onto Isabel classes. So kind star goes to class rep, and then we define an additional class called Tycon that essentially represents kind star to star. And so this is implemented by fixing some operations on the universal domain that essentially represent the type constructor. So more details about that you can find in the paper. And then finally, we also have a type application type constructor. This is really a binary type constructor in Isabel that we write with infix dot, and that is used to represent type application. So here T is in class Tycon, and then A is in class rep, and then the type T dot A is again in class rep. Okay, so once we can represent type constructors abstractly, the next thing we need to do in order to reason about a constructor class is to reason about the class constants that have polymorphic types. So in a language that has parametricity, any function that has a polymorphic type satisfies a Wadler-style free theorem. And essentially what the free theorem says is that the different type instances of that function have to behave in a uniform manner. So the idea is, for the Tycon library, we can ensure a similar kind of uniformity over type instances by defining a polymorphic function via a single sort of largest type instance, and then define all the other type instances by coercion. So we can actually coerce between any two representable types by just mapping via the universal domain. It's just embed and then project out into the new type. And so we'll see an example of how this works with the functor class. So here we have class functor. fmap has a polymorphic type that's polymorphic over type variables a and b. And so in the Tycon library, we define the functor class by basically taking the largest type instance. So we instantiate a and b with the universal domain type. And then the class method is then a monomorphic version of fmap that has that largest type instance. And then outside the class definition, we can define the polymorphic version of the function by just coercing from the larger type instance to a more specific one. And so essentially, when we have coerce applied to a function, coercing between functions is the same as coercing the arguments and then coercing the result. So so far this just covers the definitions of the constants. So we also need to think about how are we going to express the class axioms now, and how are we going to deal with the type quantification. So the easiest example to work through to show the general pattern of how to do this is this functor plus class. So essentially we have a class that's a subclass of functor, and we're going to fix an associative append operation. So we have this class law, associativity, and notice that this is actually a polymorphic law since it's quantified over the type variable a. And so we'll see if we can formalize this using the Tycon library. So this is the definition that we'll start with. So we have the type class. We fix a monomorphic version of the append operator that's at its largest type instance, and define the polymorphic one by coercion. And then we will put an axiom that is basically the same law that we wanted to show polymorphically, but we'll just have it instantiated to the specific type. But it turns out that this is actually insufficient to derive the polymorphic law by itself. So what happens if you try to prove this law at the bottom? If you unfold the definitions, you end up with a pair of coercions that go from the type t.u to the smaller type t.a and then back to t.u again. And in that context, we would like to be able to show that those coercions cancel out, but the assumptions we have aren't strong enough to do that. So it turns out we need a new law. We added a naturality law that says that the monomorphic fmap commutes with the monomorphic append. Basically, that is enough to ensure that the coercions all cancel out, and that we can transfer properties from the one type instance to any other type instance. So essentially, the naturality laws are they basically encode this type quantification. Let us state a polymorphic axiom in terms of just a single type. So the overview of the library, we have Tycon library provides the type application operators, a collection of constructor classes like functor, monad, monad plus, and so on. Those are all defined using the same technique that I showed previously with functor plus. And we have some automation for doing the definitions with coerce and transferring theorems back and forth. The other big part of the automation is we have a new package called the Tycon package. This is just like the domain package and reuses much of the same code, but instead of defining an ordinary Isabelle type, it defines a type constructor that uses that type application operator. So this is really useful for defining instances of these constructor classes. And the package also automatically defines the fmap and does most of the work for proving the functor instance. So we've used the Tycon library to verify a bunch of stuff. Verification of monads, we've done a bunch of examples. Those are all mostly pretty straightforward. You can use the standard kind of Huffman CF techniques to prove them with induction and simplification. So the interesting bits are the verifying the monad transformers. So we've done a few of those. First, the resumption monad transformer. I won't go into the details here, but I'll just mention that The proofs for this one actually work without too much trouble. The definitions are straightforward to translate into the tools, and most of the effort involved in the formalization is actually exactly the kind of things that are you would spend most of the work doing a pen and paper kind of formalization. The only difficult proof is really proving the right kind of induction principle that's used to prove all the other laws. So the error monad transformer and the writer monad transformer, things get a little tricky. So those actually, the proofs of the monad laws actually fail for those. But the automation in the Tycon library is really helpful to study in exactly how they fail. And so we can use the library to show that they actually do preserve the monad laws in a certain sense. So I'll just describe the error monad transformer in here. So this is the definition in Haskell of the error monad transformer. Essentially we start with an error monad type, and then the error transformer is parameterized by an inner monad T, and it's basically just composing monad T with the error monad. And so you can formalize this in Hull CF with the Tycon library. This is very straightforward, and the definitions look almost identical to the original Haskell code. Except we have the type parameter T is now in class Tycon. So we can go through and do most of the proofs. The left unit law holds, bind is associative. We can define lift, throw, and catch operations, and we can prove laws about those. But the right unit law actually fails. So if we instantiate M to be the value error T of return bottom, this breaks the right unit law unless the inner monad has a strict return function. Because the left-hand side evaluates the bottom and the right-hand side doesn't. But it turns out that problematic value is actually impossible to construct using any of the functions exported by the module. And you can show that actually for all constructible values, the right unit law actually does hold. So you can view error T as an abstract data type where you have this data type invariant, which is simply the right monad, right unit law, and all operations preserve the invariant. And we also need to check that recursive definitions preserve the invariant as well. So to conclude, we've done some proofs about monad transformers. The resumption transform preserves the monad laws. The error and writer transformers do preserve the monad laws if you view them as abstract types. And the Tycon library has a lot of useful automation for reasoning about these types of things. It's easy to define new type constructors. You can focus your effort on the interesting parts of proofs without having to write a lot of boilerplate. And the library is available for download on the archive of formal proofs if you have Isabel 2012. So thank you for listening.